This is the sixth video in a series covering complex analysis. And today we're going to look at sequences of complex numbers and what it means for them to converge, as well as a bunch of examples and results that follow from similar results in real analysis. Okay, so let's look at our first definition. So given a sequence of complex numbers, so I've written that sequence as C sub n as n goes from 1 to infinity. So this is just a list of complex numbers, C1, C2, C3, C4, so on and so forth. We say that this sequence Cn converges to C, and write the limit as n goes to infinity of Cn equals C if for all epsilon bigger than 0, there is an n, which is a natural number, such that if n is bigger than or equal to this capital N, we have Cn minus C. I should say the modulus of Cn minus C is less than epsilon. And this is an important thing here. These are not sequences of real numbers. So saying the absolute value doesn't really make sense. We have to take the modulus of these complex numbers. But other than the fact that we're working with complex numbers and we have the modulus instead of the absolute value, this is exactly the same definition as we would have with real sequences. And generally, since a complex analysis class is taken after a real analysis class, I hope you're familiar with calculating limits and showing that sequences have limits with real numbers. Oh, and I'd like to point out that here I'm saying that this C is a complex number. So this is not for an infinite valued limit here. Okay, so now we're going to start with a couple of examples before we review some results from real analysis. So our first example says that if we have a complex number P, where the real part of P is bigger than 0, then the limit as n goes to infinity of 1 over n to the P equals 0. Okay, so the important thing here is that the real part of P is bigger than 0. It doesn't matter what the imaginary part of P is. Okay, so let's see if we can get to this. So let's maybe set our number P equal to A plus BI, where A and B are real numbers. So in other words, we're extracting the real and the imaginary part of P. Okay, and then notice that this condition right here means that A is bigger than 0. Okay, next, let's look at 1 over n to the P in terms of this expansion as A plus BI. So we've got that this is equal to 1 over n to the A plus BI, which is 1 over n to the A, times 1 over n to the b times I. But now let's recall how this complex exponential is taken. Here we have this as 1 over n to the a. I can just write that as is, and this will be 1 over e to the natural log of n times b times I. But notice this is of the form e to the I theta, where theta is natural log of n times b. And maybe we could see this a little bit more clearly if we wrote this as 1 over n to the a, and then e to the minus natural log of n times b to the times I. But looking at this, we see that this guy right here is on the unit circle. So in other words, its modulus is exactly equal to 1. And again, that's because it's of the form e to the minus I theta. And we looked at things on the unit circle before, so this is pretty clear. So that means all we need to show is that this guy right here tends towards 0. But here we've got A is a real number, so that should follow from general strategies of taking limits of real valued sequences. So let's work through the details just as a review. So generally when you're finding a limit, you like to do the scratch work first, which is really the reverse of the calculation, and then write it out in the correct way in the final product. So let's point out that our goal is to show that 1 over n to the p in absolute values, or I guess I should say in modulus, is less than epsilon. But by this equation right here, we see that that's equivalent to 1 over n to the a being less than epsilon, its modulus. And why is that? That's because the modulus of this thing right here is 1 by our previous discussion of it being on the unit circle. But now 1 over n to the a is positive, so we don't need that modulus, or absolute value in this case, because it's real. So this is the same thing as 1 over n to the a being less than epsilon, which is the same thing as n to the a being bigger than 1 over epsilon. But let's notice that that is exactly the same thing as n being bigger than 1 over epsilon to the 1 over a. So that gives us an idea for how to pick our capital N in this definition over here. Okay, so now that we've worked out our scratch work in reverse, we're ready to rewrite this in the correct order. So let's say we are given some epsilon bigger than 0. Let's take n, which is a natural number, to be bigger than 1 over epsilon to the 1 over a. So we know 1 over epsilon to the 1 over a is a real number, and then by the Archimedean principle, there's a natural number larger than every real number. So that's how we pick this natural number n as some natural number bigger than this real number. So let's point out maybe that n is a natural number as needed. And now let's observe that if we have little n bigger than or equal to capital N, then that tells us that little n is bigger than 1 over epsilon to the 1 over a. And now we can essentially follow this in reverse. That implies that n to the a will be bigger than 1 over epsilon, which is the same thing as 1 over n to the a being less than epsilon. And now finally, we can say the modulus of 1 over n to the p is equal to 1 over n to the a by this line right here, which is less than epsilon. But now if we read this modulus of 1 over n to the p as, maybe let's be really thorough here, the modulus of 1 over n to the p minus 0, then we have achieved our result. We have pinned our sequence within epsilon of its limit. Okay, good. So that's good for this example. Let's do 2 more before we look at some previous results from real analysis. So our next example will start with a complex number called z, whose modulus is less than 1. And we'll prove that that implies that the limit as n goes to infinity of z to the n is equal to 0. So let's maybe do our scratch work, which is essentially the reverse of the proof that we want to give in the end, but it's kind of a constructive tool. So let's notice that in order for this to be true, we need the modulus of z to the n minus 0 to be less than epsilon, but that's the same thing as saying that the modulus of z to the n is less than epsilon. But then since n is a real number, well, actually maybe since n is a positive integer, we can bring it outside of the modulus. So this is if and only if the modulus of z all to the n power is less than epsilon. But now we'd like to retrieve that n from the exponent. We can do that via a logarithm. So since we're working with real numbers here, because we have the modulus of z, we can use the natural logarithm. That'll give us n times the natural log of the modulus of z is less than the natural log of epsilon. Next, we know the natural log of the modulus of z is negative because the modulus of z is less than 1. So that means if I divide by it, I switch the direction of my inequality. So that tells me that I have n is bigger than the natural log of epsilon over the natural log of the modulus of z. And let's point that out. That's because the natural log of the modulus of z is less than 0. Okay. So now I think we're good to go. We've got an idea for how to choose our capital N. It should be chosen with regard to that natural log of epsilon over natural log of modulus of z. But that being said, that only works if z is not equal to 0. So that means we need to look at the z equals 0 case by itself, but that's pretty clear because 0 to the n is equal to 0, so we won't look at that case super carefully. So now let's point this out. So for z not equal to 0 and given epsilon bigger than 0, let's take n, which is a natural number, such that capital N is bigger than the natural log of epsilon over the natural log of the modulus of z. And now observe that if little n is bigger than or equal to capital N, we have little n is bigger than the natural log of epsilon over the natural log of the modulus of z. But that implies that n times the natural log of the modulus of z is less than the natural log of epsilon. And here we have used the fact that the natural log of the modulus of z is less than 0 as the order of the inequality changed, or the direction of the inequality changed. So next we can maybe use exponent rules. That'll give us the natural log of the modulus of z all to the n power is less than the natural log of epsilon. We can exponentiate that to give us the modulus of z to the n is less than epsilon. But now we can bring this n inside. We're able to do that because it's a natural number. That tells us that we have the modulus of z to the n trivially minus 0 is less than epsilon if we take its modulus like that. But this is exactly where we wanted to end to prove this limiting behavior. Okay, so let's do one more of these maybe, and then we'll go on to other stuff. So our next limit doesn't have anything to do with complex numbers, but it's still important. And that's that the limit as n goes to infinity of the nth root of n equals 1. And we'll approach this the same way by working it in reverse to give us an idea of what our capital N should be, and then rewriting it in the correct order. So let's notice that our goal is to show that the absolute value of the nth root of n minus n is less than epsilon for some n that are larger than a certain number. That probably depends on epsilon. Notice I'm able to say absolute value here instead of modulus because we know all of these are real numbers. So now what I want to do from here is somehow create something having to do with just n, because I need my n to be bigger than or equal to something. So let's see how I can do that. Well, let's start with n, and we can notice that n is the same thing as the nth root of n to the n power. So that's writing n in terms of part of what we have up here. But now that's going to be the same thing as the nth root of n minus 1 plus 1 to the nth power. Now that might seem like a little bit too much work, but this is going to be super helpful because now we can use the binomial formula to expand that, where we're thinking about this stuff in purple being grouped together and then this number 1 kind of being on its own. So this expands as the sum, as k goes from 1 to n, of my binomial coefficient n choose k. And then I have the nth root of n minus 1 to the k power. But now I'd like to drop all of the top terms and just keep the second term. And we'll see why this is helpful. So that's going to give something that is strictly smaller, because instead of having n total terms, we only have a single term. It's the second term here. I guess we should point out that this expansion only works when n is bigger than or equal to 2, but that's totally okay because we're letting n go to infinity. So if we take just the second term here, we have this is bigger than n choose 2, and then we have the nth root of n minus 1 squared. But let's notice that's the same thing as n times n minus 1 over 2, and then the nth root of n minus 1 squared, where I just use the definition of that binomial coefficient. So now let's look at the extreme left and right hand side of this inequality that I've created, and observe that I can use it to pin this nth root of n minus 1 below something that's a little bit easier to work with. So in particular, I have the nth root of n minus 1 squared, will be less than, let's see, 2 over n minus 1. That's just from moving all of this to the other side of our inequality. But now taking a square root of both sides, we see that the nth root of n minus 1 is less than the square root of 2 over n minus 1. And now we want this thing to be less than epsilon. But maybe I'll leave this little tiny bit for you guys to do. Forcing this thing to be less than epsilon will result in having, we get that n has to be bigger than 2 over epsilon squared plus 1. So we get that just from inverting this formula right here to solve for n. So I'll leave that for you guys. And now that we've got this set up, this gives us some motivation for how to choose this capital N, and we can write down our final proof of this limit. So let's say we are given some arbitrary epsilon bigger than 0. Let's take a natural number n such that our natural number n is larger than 2 over epsilon squared plus 1. We're able to do that, again, by the Archimedean principle. There's a natural number larger than any real number. Okay, so next we can say observe that if little n is bigger than or equal to capital N, we have little n is bigger than 2 over epsilon squared plus 1. Well, so that's pretty clear just from this inequality right here. And then from there, we'll need to insert this side calculation. So I'll just say insert here this side calculation. And that will end with the nth root of n minus 1 being less than the square root of 2 over n minus 1, which is less than epsilon. And notice the nth root of n is always larger than 1. So this thing is always equal to its absolute value because it's always positive. So we can just put the absolute value there. But we've achieved the desired inequality to establish this limit. Okay, so now what I want to do is do a quick refresher of a bunch of standard results from real analysis before we move on to some results involving these complex sequences in general. So here are 3 standard sequence definitions from a real analysis setting. And 2 of these make sense in complex sequences as well, so we'll point that out when it's appropriate. So we'll go over these and then look at some results from real analysis related to these definitions. Okay, so a sequence AN of real numbers is said to be bounded if there is a real number m such that the absolute value of AN is less than m for all natural numbers m, for all natural numbers n. So nothing special about the real numbers here. This could also be complex numbers, but this m will still be a real number, because you can't really talk about being bounded above by a complex number because there isn't really a canonical ordering on the complex numbers like there is on the real numbers. Furthermore, this would be read as the modulus of a sub n instead of the absolute value, again, because we're in complex numbers. So let's see, this so that means this definition makes sense if we look at a sequence of complex numbers. So that's not true for this second definition. So a sequence of real numbers AN, so let's point out that these are real numbers, is monotonically increasing or decreasing if there is an n, which is a natural number such that for all n bigger than or equal to n, we have an plus 1 is bigger than an, so that would be monotonically increasing, and we have an plus 1 is less than an, that would be monotonically decreasing. And sometimes we don't require these strict inequalities, but we require kind of looser inequalities. And so that would involve a less than or equal to here and a greater than or equal to here. So now this doesn't make sense if we move it over to complex numbers, because again, there's not a canonical ordering on the complex numbers, so it's hard to talk about which one is larger or smaller. So for our next definition, we'll take a sequence of real numbers and we'll call it Cauchy if for all epsilon bigger than 0, there is a natural number n such that if m is bigger than little n, which is bigger than or equal to capital N, we have a sub m minus a sub n, their absolute value is less than epsilon. So again, this could be also defined for complex valued sequences as well. We could replace this r with the c The only thing that would change is that when we were to read this off, we would say the modulus of am minus an instead of the absolute value. But the definition is exactly the same. Okay, so now that we've got these definitions recalled, let's look at some results involving these definitions. So here are some results that we'd like to recall from real analysis built off of those definitions which we just recalled. And the first one says every convergent sequence is bounded. And this is one of those that will work for complex valued sequences as well as real valued sequences. And the proof is essentially exactly the same as what you would see in a real analysis class. So I'll let you guys check that out if you need to. I have a whole course of real analysis on the main channel. I'll put a link in the description. Then next, if a sequence is monotone and bounded, it converges. This is called the monotone sequence theorem. So this only makes sense for real valued sequences, again, because this monotonicity or increasing or decreasing behavior only makes sense for real numbers. Then next, a sequence converges if and only if it is Cauchy. So this works for real or complex valued sequences. Okay, so next up, I want to prove a result that allows us to tie together the convergence of a complex valued sequence with the convergence of its component real valued sequences. Okay, so this is a pretty big theorem. It says that a sequence of complex numbers converges if and only if the sequences of real and imaginary parts of that complex sequence also converge. Okay, so notice this is an if and only if statement, so we have two things to prove, but before we jump into one of the directions, I'm going to set some notation. So let's let Cn equal An plus Bn times I, where n is running over all of the natural numbers, and then we have An and Bn are sequences of real numbers. So in other words, this is our sequence of complex numbers, and these are the real and imaginary parts. So now let's jump into this forward direction. So in other words, we're going to start assuming that this sequence converges. So let's suppose that the limit as n goes to infinity of C sub n equals C. But little c is a complex number. That means I can decompose it into real and imaginary parts. I'll decompose it into a plus bi, again, where a and b are real numbers. And now what we'll do is make the following claim. And that claim is kind of obviously built off of our choice of a and b here. That is that the limit as n goes to infinity of an equals a, and the limit as n goes to infinity of bn equals b. And that'll finish off this forward direction. Okay, so let's say we're given some epsilon bigger than 0. Let's take a natural number n such that if n is bigger than or equal to n, so lowercase n bigger than or equal to capital N, we have the modulus of Cn minus C is less than epsilon. But now we'll use an inequality that we proved in one of the very first videos, and let's recall that real quick. So we're going to use the fact that the absolute value of the real part of z and the absolute value of the imaginary part of z are both less than the modulus of z. So I won't do that proof, but you can look in maybe the first or second video where we calculated that. So now let's notice that that allows us to write a sub n minus a in absolute values. That is exactly equal to the absolute value of the real part of Cn minus C, by the way that we've notated all of these sequences, but that is less than the modulus of Cn minus C by this inequality that we recalled, but that is less than epsilon. But now starting right here and producing an inequality where this is less than epsilon is exactly what we need for the limit of these an to tend to a. And I guess I should point out here that this is not a strict inequality. Okay, so let's move on to bn, but that's essentially the same thing, just using this imaginary part. So we have the absolute value of bn minus b is equal to the absolute value of the imaginary part of cn minus c, which is less than or equal to the modulus of cn minus c, which is less than epsilon. But again, starting at the left-hand side and moving towards the right-hand side, we've achieved exactly our required inequality to prove this limit. Okay, so now let's look at the reverse direction. So let's finish this proof off with the reverse direction. So we want to suppose that the limit as n goes to infinity of the real part, an, has a value a, and that the limit of the imaginary part, bn, has a value which is also b, or maybe we'll call that b, and then next we'll set c equal to a plus bi. Okay, nice. So now let's say we are given some epsilon bigger than 0. Let's choose a capital N that represents this convergence as well as this convergence, but those might be different capital N's. So I'll notate them as follows. Let's take capital NA and capital NB, which are natural numbers, such that if little n is bigger than or equal to NA, we have the absolute value of AN minus A is less than epsilon over 2, and if little n is bigger than or equal to capital NB, we have the absolute value of Bn minus B is less than epsilon over 2. So you'll see why we set these less than or equal to epsilon over 2 in just a second. So next, let's set capital N just to be the maximum of these two numbers. So the maximum of NA and NB, and this is going to be the value of capital N that gets it done. And so let's finish this off. Observe if little n is bigger than or equal to capital N. Well, that means that it's bigger than or equal to NA and NB. So that's good. And now let's do the following calculation. We have Cn minus C. Well, the modulus of Cn minus C is equal to the modulus of A minus AN plus I times B minus BN, just by addition rules for complex numbers. But now we can use the triangle inequality to write this as less than or equal to the absolute value of A minus AN. No longer do I have to say the modulus because those are real numbers. And then plus the absolute value of B minus BN. Really, it's the modulus of I times B minus Bn, but the modulus of I is 1, so that'll turn that just into absolute value. But likewise, each of these are less than epsilon over 2, so the whole thing is less than epsilon over 2 plus epsilon over 2, which is in turn equal to epsilon. And now, if you look at this side of the inequality and this side of the inequality, we see that we have achieved exactly our inequality to show that the limit of Cn is C, which is exactly what we needed. So let's get rid of this and I'll leave you with some warm-up exercises. So here are 3 nice warm-up exercises. So the first is to review the sum, product, and quotient rule for limits, as well as the squeeze theorem. So I think everything we saw today says that if you understand how sequences work for real numbers, you understand how they work for complex numbers, especially in light of that last theorem. So I think maybe looking over this from a previous class or maybe checking out the playlist that I mentioned earlier would be a good thing to do. Next, show that the limit as n goes to infinity of n cubed minus 2n squared minus 5 over 2n cubed minus 3n is equal to half. So just recall the careful way to do this using these properties up here along with something that we proved earlier. Let's recall earlier, one of the special cases of something we proved was that the limit as n goes to infinity of 1 over n equals 0. So here's another 2-part question. So for any complex number alpha, define the binomial coefficient alpha, choose 0 to be 1, and then alpha choose n is equal to this descending product alpha minus 1 all the way down to alpha minus n plus 1 over n factorial, and then calculate the following 2 binomial coefficients. So 1 plus I choose 3 and I choose 2. And then next, show that the sequence of these binomial coefficients alpha choose n is bounded if and only if the real part of alpha is bigger than or equal to -1. And that's a good place to stop.